Hi, I'm going to present parameterized projected Bellman operator to you. It's a paper that focuses on gaining sample efficiency in approximate value iteration, AVI for short. Well, AVI is a method that belongs to reinforcement learning, RL for short. In the past, it has shown to be very effective for solving very complex problems, but it still lacks of some sample efficiency. That's why we tried to tackle this problem in this paper. Well, in a nutshell, AVI is a method that can be understood in the space of Q functions that you have here. And here you have the space of representable Q functions. Indeed, in most cases, in AVI, we use function approximation, let's say neural networks. So we start with a random Q function with random set of parameters, and we apply the optimal Bellman operator. For a pair of state and action, it looks like that. So you have reward plus gamma max of this Q function that you have. And then we try to learn this new Q function that is a target, not belonging to the space of representable Q function, with another set of parameters that are called omega 1. And we try basically to minimize the distance, so the loss, between those two Q functions. The goal of the process is to reach the optimal Q function, or more precisely, to reach the projection of the optimal Q function into the space of representable Q functions. So the end goal is to reach omega star. You are then left with a sequential process that at each step takes a neural network and outputs another neural networks through a sequence of operations. So you first have the optimal Bellman operator that I defined earlier, and the projection step. For example, for each point that is not lying in the space of representable Q functions, the projection space operator is represented as follows. You also have, at the end of the training, a sequence of Q functions. And now you can spot directly two major flaws. The first one is that you have a sequential manner of tackling this problem. You are in a sort of sense greedy with respect to your choices. Another problem that I can see is that at the end of the training, we are only relying on the last Q function and not the previous ones. That could be also interesting. This is why we came up in this paper with an idea of working directly in the space of parameters. What we want to do is to learn a hypernetwork, a neural network that takes as input weights of neural networks and output weights of neural networks. This hypernetwork will look like that. At first, we would start with the same Q function, but then we would iterate over this hypernetwork to reach the first weights of this supposedly iterated Bellman iteration. And then we continue to iterate it, and we would stop at a certain point during the training. As we do with AVI, this would correspond to our budget, our computational budget. And then we would keep iterating, hoping for the best, so hoping for the fact that it would reach the optimal parameters. Well, we will see how we do that, but one key aspect that we already see is that at the end of the training, we are not stuck at this point here. We can leverage what we learned before, so basically the operator, to keep iterating it until its fixed point. How does it work in practice? So for the ones that are familiar with AVI, you directly notice the loss of the first Q function, and then you know that it's going to be iterated. So first we have basically the distance between those 2 points over the samples. And for PBO, what we noticed is that we can actually not only consider one Bellman iteration, but several, since we have an idea where the operator would go if we apply it twice and not a single time. This allows us to consider a way-reacher loss that is parameterizable, because we can parameterize the amount of Bellman iterations that we would like to consider with this parameter k. This will, of course, change the course of the training, and we will try to study that in future slides. So the second key aspect of PBO is that it takes into account in the loss several Bellman iterations. And this is very interesting because it is linked with the theorem on error propagation for AVI developed by Paramount in his PhD thesis. In this theorem, we can see that the distance between the optimal Q function and the Q function at stage k is hyperbounded by a complex term. But a part of this term is quite straightforward. It is basically the sum of the approximation errors. I have to say that it's weighted, but for now we consider that alpha k equals to 1. And we can see that the small terms represent the loss of AVI, and the sum of terms is actually represented by the expectation of this loss here. In other words, PBO takes into account several Bellman iterations or several terms of the bound on error propagation for AVI in a single gradient step. We tried to empirically validate our intuitions. By doing so, we first started on the chain walk environment. It is a Markov decision process, MDP, where you have a lot of states chained together, and they are all the same. They yield a reward of 0. And in each state, you can either choose to go left or right, and this action will be executed with a certain probability that is written here. The only states that are giving you a reward of 1 is the terminal states at the extremum of the chain. Well, we represented here 3 experiments corresponding to 3 different values of k, and each time we represented the distance of the learned Q function to the optimal Q function. So here you have at which stage of the training we looked at. So either after 2, 6, or 11 Bellman iterations. But the computational budget here was only 2. So the baseline, FQI, is stuck, as I said before, at k equals 2. But it is not the case for our 4 different approaches that we developed that are all trying to learn a PBO, because we can keep iterating after the training. You can see that in each experiment, we were able to lower this loss or this validation metric by keeping iterating the PBO. This calls back to this graphic where we showed that our intuition that the PBO could lead us to the optimal weight is true. And then we tried an offline setting where this time we are investigating the Cornhill environment. You can see that we did the same. So we tried 3 different experiments with 3 different values of k. Each time you have the average return as the y-axis and the Bellman iterations at the x-axis. You can see the computational budget represented here in a sharp black line. You can see that for our baseline, FQI, the average return is lower than for PBO. So the PBO is learned this time by the algorithm that we call ProFQI. And this has a different behavior. Now, after the training, PBO does not lead us very much closer to the optimal set of weights, but what it does is that it has already been reaching a better performance during the training Bellman iterations. And this is done, I mean, we explained that from the theorem that we just cited, that the loss is richer. And you can see it through the policies. So here we plot the policies for the PBO that is learned and for the FQI method. And you can see that PBO is performing better and the policy is clear. Well, now we tried on 2 more complex environments that are online. And the 2 previously discovered behaviors happened. Here you also have the average return with the computational budget, and the same for Luna Lander. Now we are online, so we compare against DQN, and you can see that for bicycle, it really played the role the fact that we can keep iterating the learned PBO after the training. And for Luna Lander, it was more during the training that we could see a peak in performance. Well, to conclude, we developed a method in this paper that considers several Bellman iterations at once, and also that can allow this quantity to be iterated after the training. And this is very important. Well, then for future directions, we can consider scaling PBO to more complex environments, or understanding the behavior of PBO after the training iterations, that it's still not clear for now. Thank you for your attention.